We'll end Module 3 with a brief discussion on bivariate data. The idea here is to try to plot data and fit curves to it. This is a huge subject in statistics. Sometimes it's called regression theory. We'll focus on just very basic ideas, mainly intuitive ideas. So here we have a model data set. I have bivariate data, meaning that there is an x value and a y value. So our data look like, for example, collections of pairs of points. So maybe something like 1, 2 is a point. It looks like maybe 2, 3 is a point, and so on. So I have data that has two different components, hence bivariate. The interesting question for us is, can we understand the relationship between the two components? We'll focus on the case where there's a potentially linear relationship, since it's by far the most classical, most well-studied, and easiest to do for our level. So if I look at my data, it might be possible to try to fit a single line that well summarizes the data. This is called a regression line. In this course, we don't focus on the techniques used to compute the line. It's typically done by minimizing the least squares error. We won't discuss that in any more detail. It is extremely well studied. We'll focus on what it means intuitively and how to interpret this line. The idea is that if the line fits the data well, then we can interpret the slope as giving a positive correlation between the two variables. That is, if one of the variables increases, the other one will also increase. If the slope is negative, that indicates a negative correlation between the two variables, meaning that if one variable increases, the other one is likely to decrease. This only makes sense if the variables actually have a linear relationship, i.e., the regression line is a good fit. If the regression line is a bad fit, it could mean that there's no linear pattern in the data, which means that our analysis is not useful here. One can quantify the strength of the core of the line. That is, one can estimate how well it summarizes the data. This is done with something called the correlation coefficient, which would typically be studied in a first-year statistics course. We will not discuss it. So let's do a little bit of qualitative analysis. I'm going to draw some simple data sets, and we'll try to understand if there's a linear pattern or not. So here's one. So we ask ourselves, is there an evident linear pattern? That is, we're going to try to fit a single line to the data. In this case, I think it can be done fairly well. So I would say that there's a strong positive linear correlation. We can look at another data set. Again, I'm just kind of coming up with these on the fly. So how about this one? So we ask ourselves the question, is there a linear pattern in the data? I claim no. So if I try to draw a line, none of them really work very well. There's no linear pattern. Which is not to say that there is no pattern. I think most people would be able to say that this looks a lot like a circle. There is a pattern. It's circular, not linear. So keep in mind that the analysis of bivariate data that's typically done at this level is only looking for linear fits. Anything more complicated is not done. Okay, so let's look at another example. Here, we're going to draw some data, and I'm going to tell you what the slope of what the regression line is. So let's get the data here. Okay, so here's our kind of synthetic data set. And then the line is maybe something like this. So here is y equals 8x plus 7. So first, let's try and understand whether this line is a good fit or not. Does it represent the data? Well, I would say yes, but not incredibly well. So data has a positive linear trend, but it's not a perfect trend. There are what you might call outliers, points that I'm going to circle in green here, that very strongly buck the trend, and also noise points that are close to fitting the trend. I'll do this in purple. So noise points are close to fitting the trend, but don't quite sit on the line. So you can think of noise points as maybe, we mismeasured something or kind of minor fluctuations in the pattern, whereas outliers are big fluctuations from the pattern. Outliers are very difficult for us to deal with our method. So when you're asked to interpret the quality of a regression line, it can be helpful to make comments about things like outliers and noise. It indicates that you understand that although the general trend may be in correspondence with the information given by the line, there are sort of errors in the measurements, perhaps, or there is something that our regression line is not capturing, like outliers. Okay, and then we want to interpret the slope and y-intercept of the line. That is, we want to interpret the slope 8 and the y-intercept 7. So for this, it's helpful to go back to the definition of the data. We are recording the weight of dogs as a function of time. So the slope is the rate of change of weight of dogs per, let's look at the units here, per unit time. So perhaps we're measuring in, say, years. So the average rate of change of the weight of a dog per year is something like 8, according to our data. And then the y-intercept would be equal to the weight of dogs at time 0, i.e. at birth. Okay? So our y-intercept and our slope here are estimations of the average rate of growth of dogs' weight, and in the case of the y-intercept, the average birth weight of the dogs. Keep in mind that both of these are just estimates. I took some data and I tried to create summary statistics related to them. They're not necessarily precise. We would need potentially more data to be able to do it more precisely.